Today we're going to be looking at this simulation for calculating the empirical formula of a hydrate and the percent composition of water in the hydrate. And so the typical formula for a hydrate, if you remember, is it's like a ionic compound formula here, and then there's a dot, and then there's some number, and then H2O. So that means that there's some number of water molecules locked in per formula unit into the crystal of the ionic compound, and by heating, which is what this triangle over the arrow means, or applying heat, the water is going to be evaporated off into a gas and it'll leave behind what we call the anhydrate, which is then just the ionic compound. So this is copper 2 sulfate. We're going to be trying to figure out how many waters of hydration are attached. And so our initial mass is 0.1806 grams for the hydrate. And again, we don't know what exactly the formula is here. And that's what we're going to try figuring out. So this simulation shows an open dish and a Bunsen burner. We will not be using a Bunsen burner for the lab that we do, but either way, it's a heat source, drives off the water, and let's see what happens. So it's not really relevant how long it takes. We just want to make sure that we heat it to a constant mass. Notice that copper sulfate, the sample in the dish here, is actually turning white, whereas it started as blue. And I'm just going to pause the heating because it already gave me the final mass. If you're doing this in real life, you'd want to heat until you got to a constant mass, which would indicate that all of the waters have been driven off. Likewise, if we were taking these measurements in a real lab, since the sample would be staying in the, well, in this case, this is an evaporating dish, but whether it's in a beaker, an evaporating dish, or a crucible, you would need to subtract off the mass of the empty dish itself. And so these numbers are giving us are just straight up the masses of the hydrate and the anhydrate left over. So we do need to be careful about that difference in a real lab setting. Okay, so let's look then at our calculations. So I'm going to start with the starting mass of the hydrate, 0.1806. And again, these are going to be in grams, and since I'm going to do my calculations in the spreadsheet here, I'm not going to put my non-numerical values into the cells, so I can still do calculations with the cells. So mass of anhydrate after heating, 0.1154. All right, and that is, of course, grams. Okay, and so the mass of water removed, well, that's obviously going to be the difference between the two. So I'm going to do the mass of the original hydrate minus this one. Minus that one. Okay, so we're doing the top number, original mass, minus what's left over. So that difference has to be the mass of water that left. Again, watching significant figures, since this balance from the simulation gives us 4 decimal places, when we subtract, our number also keeps 4 decimal places. Now notice that these are actually 2 leading zeros here before we get to our first non-zero. So even though these numbers started out with 4 significant figures, based on my subtraction rule, I keep the 4 decimal places, and I now actually only have 3 significant figures when I go on to use this mass in a calculation. So be aware of that. Okay, so what we want to do is, well, again, we're trying to find a formula. So we know that formulas have to do with the count of atoms, and so instead of counting individual atoms, we're going to be counting moles. And so we're going to be trying to figure out the ratio of moles of the formula unit of copper 2 sulfate to the moles of water. So we're going to find the molar mass of the anhydrate. Since we know the formula is CuSO4, I'm going to look up the molar masses of copper, sulfur, and oxygen. And there's my periodic table. So copper, again, we want to keep at least as many digits as the numbers we're working with. So I'm just going to take this whole number off the table here, 63.546. Where is my thing here? Okay, so 63.546 plus sulfur, which is right here, is 32.066, plus we have oxygen, which is 15.999, and there's 4 of them, so I'm going to factor that in. So there's my molar mass of the anhydrate. I'm going to do the same thing for water, and again, these are going to be in grams, and that's the mass equivalent to 1 mole. So for water, we've got 15.999 for oxygen, plus Hydrogen, there's 2 of them, and that's 1.008. And there we go. Okay, so just like we did in our in-class calculations, if I want to find an empirical formula, I'm going to take my masses, and these are experimentally determined masses, and I'm going to convert to moles to find the mole ratio. So again, in this case, we're not dealing with single atoms like we were in the empirical formula problems. We're going to be using the molar mass for the, again, we want the ratio of the formula units of the anhydrate to the molecules of water. So that'll be one little difference here. So we want to take the mass of the anhydrate. So this is literally just CuSO4. So that's what was left over in the bowl. So this mass divided by molar mass is going to give us moles. So we want the moles of CuSO4. And so we're going to take the mass of anhydrate, 0.1154, divided by the molar mass of the anhydrate. Again, the anhydrate in this case is CuSO4. If you have a different anhydrate, then you would be using the molar mass for that. And so this gives me moles. And again, this mass of anhydrate has 4 significant figures, so I want to make sure that I have 4 significant figures on this one. So let me fix that up. There we go. And this now is moles. Same thing, we're going to do moles of water. And so we want the mass of water. So that is this. That's the mass that we drove off, the difference between the starting and the final mass. And divide that by the molar mass of water. And there we go. Again, though, this number only had 3 significant figures from that subtraction. We lost one, so we want to make sure that that's how we report that. Okay, so the next thing we do when we're finding empirical formulas is to divide the smaller, or divide the mole amounts by the smallest mole amount. And that is so that we can hopefully come up with a whole number ratio. So of these 2 numbers of moles, the smaller of the 2 is copper sulfate's moles. So I'm going to divide each by that number. So I'm going to do this number divided by itself, and that gives us a 1. And I'm going to do this number divided by that small number as well, and that gives me 5.00. So this is our mole ratio. And so that means that, luckily this is a whole number. It's coming out very, very close to a whole number. And again, experimentally speaking, you know, your numbers might not be as perfect, but again, we're looking for a whole number at this step. And pretty much for hydrates, it's going to be a 1 to some number water molecule ratio. There's usually never, actually there never is a coefficient on the formula mass of the anhydrate. So, sorry, the formula unit of the anhydrate. So our mole ratio is 1 to 5. So that means then that if I want to write my formula, it would be CuSO4. And I do need to insert a special symbol to get the dot. Where is it? There we go. And get that out of there. And then that will be 5H2O. Okay, so that's going to be my final empirical formula. Again, it's a 1 to 5 ratio of copper sulfate to water. And there's the answer to the question of what's the empirical formula of the hydrate. The other thing we'll have to do is find percent composition. And although you now have a formula, which is a pretty good match to this data, we should be using experimental data to find the mass of percent composition. So if I want percent composition of water, I'm going to use the mass of water. That's the thing we're interested in, the percent of. So I'm going to take the mass of water, which I found here, so 0.0652, divided by, so we need the total mass of the hydrate itself, right? Because this water contributed to this mass of 0.1806 grams. And then remember that we're going to multiply by 100 to make it a percent. And there you go. And again, if my mass of water only has 3 significant figures, we should probably leave this at 3 as well. So that's 36.1. And again, the units would be percent. And there is your percent composition of water for this hydrate.